Hello viewers, in this video we will discuss the architecture of 8086 microprocessor. We already discussed in the first video what is a microprocessor. So we know it is a silicon chip which includes arithmetic and logic unit, ALU, register circuits and control circuits. So what is the definition of a microprocessor? It is a programmable electronic device that accepts numbers. Number here it is binary number, and it performs some operations, arithmetic operations or logical operations on the accepted number and according to the program stored in memory, and then it produces other numbers which is the output. It is called as the result. Some features of 8086. First we will see what Intel 8086 is a 16-bit microprocessor, and it is used as a CPU in a microcomputer. What does this 16-bit means? It is nothing but the ALU, internal registers, which are present in 8086 microprocessor, and most of the instructions designed to work with the 16-bit binary word. The word WORD, it is nothing but 2 bytes or 16-bit number. It is a 16-bit number. That means the size of the ALU, arithmetic logic unit, and the size of the internal registers in 8086 microprocessor are 16 bits. Next we will see it has 16-bit data bus and it has 20-bit address bus. Because the address bus is 20-bit, the memory address is also of 20-bit size. It requires only just 5 volts power supply. Next we will see in detail about the architecture of 8086 microprocessor. In this now we will discuss we will see now the block diagram of the 8086 microprocessor architecture. So first it has 2 unit, bus interface unit BIU, and the second one is execution unit EU. And now we can see it has general purpose registers in green color, AHAL, BHBL, CHCL, DHDL. These are the set of general purpose registers. And then we can see special purpose registers, ES, CS, SS, DS, IP register, and then we have SP register, BP register, SI register and DA register. These are all special purpose register, and it also contains ALU, operands, flags, flag registers, control systems. It has 6 byte 1, 2, 3, 4, 5, 6 instruction stream byte queue, and then you can see the summation which computes the 20-bit physical address and then memory interface. So we will now discuss one by one these 2 functional units. So just now I mentioned 8086 microprocessor is divided into 2 independent functional unit, that is bus interface unit BIU and execution unit EU. Now we will first discuss the functions of what are the functions of bus interface unit BIU. So this BIU computes 20-bit physical address for memory access. To access a memory, it sends this 20-bit physical address on the address bus, and then it fetches up to 6 instruction bytes from the memory for the following instructions. That means next instructions. It stores these instructions bytes in prefetched bytes in, first out register set. We call this register set as instruction queue or simply queue. Just now we saw in the block diagram 1, 2, 3, 4, 5, 6. Next comes, it reads data from the ports and memory. We will see what is a port later. It also writes data to the port as well as to the memory. Next, we will see, we saw that 8086 contains 4 segment registers: code segment register CS, data segment register DS, extra segment register ES, and then stack segment register SS. Next, these 4 segment registers, CS register, DS register, ES register, and then SS register, all these registers are used to hold upper 16 bits of starting address of memory segments. So, here in 8086 microcomputer, memory is divided into 4 logical segments. Memory is divided into 4 logical segments: code segment, extra segment, stack segment, data segment. Okay. So, based upon the segment registers. So, next we will see here instruction pointer IP. So, this instruction pointer IP is in bus interface unit, and it is used to hold 16-bit address, and this address is called offset address of next code byte within the code segment. Just now I mentioned memory is divided into 4 segments, logical segment, code segment, data segment, extra segment, and stack segment. These are all logical segments. So, in code segment we will store data as well as the instructions. So, the IP register holds the 16-bit address. This 16-bit address is called offset of the next code byte within the code segment, not the current instruction. It is the address of the next code byte. Now we will discuss how to compute a 20-bit physical address. So, for that one, to compute 20-bit physical address, that is for memory, the format is segment based address and offset address. The format is segment based address and offset address. Now we will assume that the code segment register contains 4 zeros, and this is the thing, but the starting address of the code segment, and then we'll assume that the instruction pointer IP contains 1008, and this is offset address. You see, both are 16-bit address. With the help of these two 16-bit address, what are the two 16 address? Two addresses: segment based address, offset address. This is what we mentioned as the format: segment based and offset address. How to compute now? How to compute 20-bit physical address? So, this 4 zeros now becomes 5 zeros. I have shown in red color. So, 0 is appended to the, in the last, 0 is appended as the last 0, and then we will, this is, now this becomes 20-bit segment based address. Now this becomes 20-bit segment based address, and then we will add the instruction pointer content 1008. Now if we add these two, it becomes 101008. This 01008 is the 20-bit physical address, of the memory. This is how to compute a 20-bit physical address for the code segment. Similarly, for data segment and extra segment, we can calculate the 20-bit physical address. Instead of CS, we have DS, and we have the offset address for data segment and for extra segment. Okay. Next, we will move to the execution unit. Now we will discuss what are the functions of the execution unit. So execution unit, before discussing the function, so it contains control circuits, it contains decoder, which is not shown in the block diagram, it contains general purpose registers, we have seen that one, it contains ALU, that also we have seen, it contains pointers and index registers, that also we have seen. So these two comes under special purpose registers. And then we saw flag registers. And now what is the function of control units? Now we will discuss the functions of execution unit. So control circuit, it directs internal operations. All internal operations of the microprocessors are controlled by the control circuits. Next comes the decoder. It translates the fetched instruction from the memory into series of actions that the EU execution unit carries, it performs. Next is ALU. It performs arithmetic and logical operations, addition, subtraction, logical OR, logical AND, logical XOR, performs increment operation, it performs decrement operation, complement operation, shifting of the binary numbers. We have just mentioned few arithmetic and logical operations as an examples. Now we will see general purpose registers. So the 8086 microprocessor has 8 general purpose register: AH, AL, BH, BL, CH, CL, DH, DL. All these registers are 8-bit registers. That means it is used to store only 8-bit data temporarily. Then comes AL register, is also called as the accumulator because it has some extra features, because it can, we will discuss this later. Next, some acceptable register pairs in the case of general purpose register are AH and AL can be paired, and it is referred to as AX register, and we can pair BH and BL, which is referred to as BX register. Similarly, we can pair CH and CL, and this pair is referred to as CX register. And finally, we can pair DH and DL registers. That means we can combine these registers to form a pair, and this DH and DL pair is referred to as DX register. All these registers, AX register, BX register, CX register and DX register, are used to store 16-bit data, whereas AH or AL or BH or BL, CH or CL, these are used to store only 8-bit data, not 16-bit data. Next, the advantage of using internal register. What is the advantage of using internal register? So this advantage is we can more quickly access these registers than the external memory, because these registers are internal to the microprocessor, whereas memory is external to the microprocessor. This we already discussed in the first video. Memory, input device, output device are external to the memory, so it requires extra time for accessing memory, for accessing input, for accessing output. If we use internal register, the time consumed for accessing the internal register is very less. Next comes pointers and index registers. So there are the stack pointer SP, base pointer BP. These two are called as pointers. Remember, we already discussed IP, instruction pointer. This is also a pointer. So, and then comes source index SI, destination index. These two are nothing but index registers, and SP and BP are nothing but pointers. And we should also remember that IP is also a pointer. All these are 16-bit register which are used to store or hold 16-bit data. 16-bit data. So these are all used to store or hold 16-bit data temporarily, like general purpose registers. Next, it is mainly used, these pointers and index register are mainly used to hold 16-bit offset address, 16-bit offset address of a data in one of the segments. We mentioned segments. There are four types of segments, four types of logical segments: code segment, data segment, extra segment, and then stack segment. So the offset address of these four logical segment is stored in these registers. Now we will discuss about the flag register. Flag registers are very, very important register. Why? Because these are used for decision making. These are used for decision making. Now we will see what is a flag. Flag is a flip-flop. We studied flip-flops in digital circuits. Flip-flop is a 1-bit storage device. Flip-flop is a 1-bit storage device. So it indicates some conditions produced by the execution of the instruction, or it controls certain operations. There are two things here we have mentioned. One is it indicates the conditions produced by the execution of an instruction, that is ALU, arithmetic and logical. After performing the arithmetical or logical operation, the conditions are changed, or it controls certain operations. Now we will see those things now, flag register, later. Now we will see the animation of fetch, decode, execute operation for add AX, BX instruction. Please remember or note, all the instructions of the program are stored in code segment of the memory. Fetching is nothing but getting the instruction from the memory. That operation is called fetching. After fetching, that instruction is decoded and then executed. Execution means performing the addition operation, AX, BX. So before an animation part, 20-bit physical address, how it is computed. So segment base, offset address. Segment base is for the code segment. So we have taken the actual value. Segment base for the code segment, which is the starting address of the code segment, 4 zeros, and 1008. It is the offset where the add instruction is stored. So you can see in this picture, offset address 1008 is the offset address for the machine code 0108, for the machine code or opcode or operation code add AX, BX. So this instruction is 0108. This data or this instruction is stored in the memory, which is brought inside the microprocessor. That operation is called fetching operation, and then it is decoded and then executed. So what we will assume is 16-bit data 1, 0007 is in AX register, and then 16-bit data 2 is in BX register. After addition of these two data, 0007 and 0002, the result will be in AX register. This AX register is called as a destination register. Now we will see the animation part. We know this is nothing but a microprocessor architecture, and you can see here 4 zeros is the 16-bit segment base for the code segment, and then 1008 is the offset address for the add AX, BX instruction. And then you can see 0007 is data 1, which is in AX register, and then we can see 0002 is the data 2, which is in BX register. We want to add these two register, and we will see that operation. So this side we have memory, this side we have memory. So we have even memory which has only even address, and then odd memory which has only odd address. Both even memory or odd memory can store only one byte in one memory location. Only one byte, that is only 8 bit. It can store only 8 bit. If we want to store 16 bits, we need both even memory and odd memory. Now this is the memory address, 16 bit memory address. So first one, 5 zeros, it is the even address, it is for even memory. Then 401, it is the odd address which is for odd memory, and then again we have 402, and that is for even memory, and then next 403, it is for odd memory. Likewise, you can see all even address is for even memory, all odd address is for odd memory. If you want to access 16-bit data or 2-byte data, we need both even memory as well as odd memory. Now the add instruction just now we saw, it is nothing but D801. This is the opcode for the add AX comma BX. This opcode is brought inside the microprocessor and then decoded, and after then it is executed. Next we will see the connections between microprocessor and the memory. Remember, the address bus and data bus are multiplexed. We have to generate separate address bus and separate data bus. For that we need address demultiplexer as well as data buffer. Address demux. So the connection address bus is connected and data bus address bus is connected, and then we have separate address bus which is connected to the memory, separate data bus which is also connected to the memory, and other connections are required, and which is nothing but address decode logic, so which generates CS bar. CS bar is nothing but chip select logic, which is simply a logic 0. It is simply a logic 0 which is used to enable the memory. CS bar is used to enable the memory. And then one more is required, so which is shown here, memory read, memory MRD bar, MRD is memory read. So this is also logic 0. These are the connections required to connect microprocessor IC with the memory. Remember, memory is external to the microprocessor, whereas all registers are internal to the microprocessor. Now we will see the first thing is computing 20-bit physical address. You can see down. So what is the operations performed one by one is mentioned here down. Step 1, step 2, step 3. So we can see that one. First is computing 20-bit address. So you can see here 4 zeros of the CS and 1008 of the IP. They are moved to the physical address computation block. Now next, this 16-bit address becomes 20-bit segment base. 16-bit address or segment base becomes 20-bit segment base inside the BIU, inside the physical address computation block, Now these two are added and we get 20-bit physical address. And this 20-bit physical address 01008 is sent on the address bus, and then we get the data. 1008 is sent. So you can see here sending 20-bit physical address. Next step is generating and sending chip select logic. 0 is enabled. So 0 is generated and it is sent to the memory. Next, memory read control signal is generated and then sent to the memory. Okay. Now opcode is sent on the data bus. Opcode 01D8 is sent on the data bus. So it comes to the instruction queue. After that, decoding. So once it goes into control system, decoding operation takes place. After decoding, operation performed. Addition operation is performed. So for that one, first data 1 007 is moved to ALU. Next 002 is moved to ALU. Now these two datas are added and we get the result 009 in the ALU, and that is moved to or copied to AX register. One second. So finally, the destination register contains the result of adding two numbers 007 and 002. In the next tutorial, microprocessor part 3, we will discuss in detail about 8086 microprocessor flags with demonstration.